similarly, okay. So here, what happens in LSTM, when we use LSTM, see RNN, you have a problem. So I told you RNN, what type of problem we usually encounter. I'm not going to write anything. Observe the board clearly, because this is somewhat a bit of huge architecture. So just written it here already. You just have explained. So observe. See, RNN has some problem, that is it has vanishing exploding vanishing gradient problem and exploding gradient problem is there in RNN, right? So RNN, you have both vanishing gradient problem as well as exploding gradient problem. So what happens? So we need to avoid this vanishing gradient problem as well as exploding gradient problem needs to be avoided. So in order to avoid this vanishing gradient problem and exploding gradient problem, we use this LSTM. What is LSTM? So LSTM means it's a long short-term memory network. Long short-term memory neural network. What is this long short-term memory neural network? See what happens here. Here means there is a chances. See, for example, let us say you have a neural network. Okay, so you have RNN. Let us say you have RNN. So you have initialized the neural network RNN, and the weights are 0.5. Weights are 0.5, 0.5, 0.5. So look at this. So weights are just, this is what RNN, right? So this is how the long, see, one after the other, one after the other, one after the other, one after the other. So what is happening here? So one after the other, one after the other, what is happening? So it's a sequential network. Apart from sequential network, so you have to initialize the weight. Suppose let us say weight is equal to 0.5. You have initialized the weight as 0.5. So now input value you are going to give. Yesterday I have given, I love my India, I gave an example. So that you were multiplying with the same weight, 0.5 W. So 0.5. So input into so what you are going to give, what you are going to get. So input, you are going to multiply that by 0.5, means so for example, let us say there are about 50 words or 50 different sentences or documents you have. So 50 times you want to check, 50 words you want to check. So 0.5 to the power of 50, what happens? So 0.5 to the power of 50, it's a very value. So 0.5 to the power of 50 value is close to 0. So what happens? You'll end up with vanishing gradient problem. Means weights are not getting up, even the weights are getting updated. So but the actual results will not reach to global minima. Actual results will not reach to global minima. So in order to overcome all this, so what we have done, in order to overcome all this, so we have introduced a new network called as LSTM. So in LSTM what happens? Just in LSTM what happens? Similarly, for example, if you initialize the weights greater than 1, you can initial weights to the neural network. You have to assume, right? Yesterday also we assumed, we initialize the weights. Initialize if the weights are less than 1, that is 0.5, you will end up with vanishing gradient problem in a recurrent neural network. Similarly, if the weights are greater than 1, for example, if the weight you are going to assume it as 2, so input into 2 power 50, there are 50 words, and the input weight you assume is 2 to the power of 50, there is a huge number, the gradient will explode. So there is a problem that what happens, there are chances that this is going to explode, and if the weights are initialized less than 1, then what is going to happen? The weights will vanish. So both vanishing gradient problem is there and both exploding gradient problem is there in recurrent neural network. So this has to be overcome. So this we need to overcome, right? So how you are going to overcome this? How you are going to overcome this? So in order to overcome, now I have to use this neural network. What is that neural network? what is that? I have to overcome this neural network. I have to design a new network. That network what we design, that is called as uh, this LSTM. This vanishing gradient problem will not be there. Exploding gradient problem will also not be there. So for that reason only we use this neural network. Okay. So here what is this? 1 minute. I just want to draw. Uh, okay. So now what's this option here? Okay. Okay. So what happens here? So this is a neural network. Neural network was something like this. One after the sequential. So what is that sequential you are having? So this is x1, this is x2, this is x3. All weights are initial w, w, w. So this is going there, this coming out of, going there, coming out, going there, coming out. So this is hidden layer 1 at time t is equal to 2, this is hidden layer 2 at time t is equal to 2, and this is hidden layer 3 at time t is equal to 3. So like this the things were there, right? So like this the things were running. So now what is happening here? I have to initialize the weights in RNN. I am talking about the RNN only. So in RNN what was happening? The weights were there. The weights used to assume. Someone wants to join. Okay. So in RNN what was happening? The weights were there. So x1 is x1 into w. So x2 into w, x3 into w. This is hidden layer number 1, hidden layer number 2, hidden layer number 3. So when you want to, so initially what you have to do, you don't have any other option. You need to initialize the network. Means, and what you have to do, along with this input what was there, you are assuming O naught x. Similarly output is the hidden layer 1. Output coming out of the hidden layer 1 is O1, and weight I am going to assume it as W1. Here W dash. So you are initializing W also, you are initializing W dash also, W1 also. This we did in your last class. So W, this is the initial weight that you are going to, this is the normal weight. This is the weight of the hidden layer. What is this? This is the weight of the, weight of the input. So W is common. W dash and W1, yesterday I told you, these are the weights of the hidden layer. Weights of the hidden layer. So you need to initialize both the weights. Means at the beginning of initialization of the network, you have to assume certain value for weights. Okay. That if you are going to assume the value for weights less than 1, so what happens? So let us say if it is 0.5. Yesterday we initialized with 0.5, right? So what happens? So that is what I am trying to say here. So if it is less than 1, so if the initial weights assumed is 0.5, what happens? Input, but input into, so input means x11, input means x11. So I cannot write here, I will write it here. Input is input into weights to the power of number of words, to the power of number of words. So this is how this, so input is x11 into weight to the power, for example 50 words are there, so you are going to say, yesterday I just assumed only 4 words, right? Usually it is not like this. A sentence several words, let us say a long sentence having some 50 words. So input value, let it be any kind of value. So weight is the weight I have assumed as 0.5. So 0.5 to the power of 50. So you just calculate this with the help of your calculator. So what happens? So obviously this value will be very close to 0. The value will be close to 0. So this value is going to be close to 0. So what I have to do? This causes vanishing gradient problem. Similarly, if the weights assumed is not zero point 0.5 greater than 1, let us suppose, let us assume the weight is greater than 1, let us say 2, the value I am going to assume it as 2. So, 2 to the power of 50, how much you calculate and check, I don't know the value, maybe the value is too high. So, this will cause the gradient to explode. Means when the gradient explodes, it is not going to reach the global minima. What will happen? So, if the gradient is going to explode, it is going to jump like this. When the gradient is going to vanish, it will never reach global minima. So, these problems are part and parcel of recurrent neural network. So, in order to overcome this, a new architecture people plan to overcome this. That architecture is what we are using as LSTM. What is this called as? LSTM. So, what is this LSTM? This is RNN. So, today, long ago, yesterday. So, long ago was there. Yesterday, look at this. Look at this figure on my left side. So you see sequential. You have 5 boxes, one after the other, one word after the other word, one word after the other word, one word after the other. You said something long ago, and that is not given importance. What you said yesterday, that is more important. Means RNN gives more importance to the immediate previous value rather than the previous value which was there, which was present long ago, right? So, but it's okay, you have to do like that, but sometimes you cannot just judge the output based on just the immediate uh, previous input that you are getting in. You need to analyze the uh, whole network. You need to analyze the whole network means you need to analyze as a context. So you need to see the context in what way you are saying. Means even the long ago whatever you have said, that also has to be given some sort of weightage. So for that reason, what we are going to use, we are going to use this recurrent LS. So what is this? Long short term memory. It's looks like it's a bit complicated architecture. Yeah, please carefully listen. Uh, I have to make you people to understand. Yeah, at the beginning you might get some sort of confusion. That should not happen. I will clear it. What is that? See, in LSTM you have two this one. Okay, one is this is whatever I am drawing here. You just observe. You have two. This is a long term. This is short term. Okay, the one at the bottom is used for updating the long short term memory, right? So the one that is there at the top, I will use this is a grid. I will use to update the long term memory. Okay, so means there is a balancing act you need to do for both long term memory as well as for the short term memory. Short term memory means what I said yesterday, long term memory means what I said 1 week ago. So both have some value, both you need to remember. So okay, because that is how LSTM is going to work. So here, see, if you look at this, you forget about everything. See, you just remember this figure. So whatever I am selecting. See here, so many things are there to remember. So three parts are there in LST. Three parts are there. So what is, so here one block you have, intermediate block you have, and the final block you have, right? So in this first block, we call them as forget gate. What is this called as? Forget gate. And another one is called as the input gate, and this one is the output gate. So we divide the LSTM architecture into three categories. One is the forget gate, another one is the input gate, and another one is the output. So in RNN, if you remember, in the hidden layers, What was the activation function used in the hidden layers in RNN? We use ReLU, we use tan hyperbolic x, right? But here in case of our, and at the output we use sigmoid, and the output we use sigmoid. But in case of LSTM, we only use sigmoid activation function as well as tan hyperbolic function, both in the hidden layers as well as the output layers. When and where, how it is going to be used, that I am going to tell you now. Okay, so here, what happened here? 1 minute. So here now I want, now understood in LSTM how many gates are there? Input gate, forget gate, output gate. 3 gates are there. See, first one is a forget gate, second one is a input gate, third one is a forget. So now I will come back here. See, why I am unable to, I can see this is somewhat, I have taken some screenshot and to make you people to explain. Even that video also I will send. Okay, you can understand there. But anyhow, you listen first. So here, what I am going to do, I told you the one at the bottom is for short term, and the one at the top. See, the one at the bottom line is for short term, the upper line is for long term, updating the long term. See, forget gate. In the forget gate, inside the forget gate, you have sigmoid activation function. What you have? You have sigmoid activation function. Inside the forget gate, you have sigmoid activation function. Means here what happens, whatever the input, so how it is coming, input will come from here, input will come from here. So sigmoid activation function will be there. So look at this input, sigmoid activation function, then output will be going. Okay, so let us see now. See, what happened. Okay, you have this sigmoid activation function. So already you know sigmoid activation function, it varies from 0 to 1. Tan hyperbolic function already you know, it varies from -1 to +1. When for example you pass on some value like 1 inside the tan hyperbolic x or tan hyperbolic theta. So tan hyperbolic of 1 is how much? How much? And if you pass on -10, how much? So look at this sigmoid activation function, just for your understanding. E power x by 1 plus e power x, correct? Already you know sigmoid activation function. So for example, if you pass on, let us say you pass on some value, so let us say 10. If you pass on e power x is equal to 10, e power 10 by 1 plus e power 10. Point means almost close to 1, 0.9995. For example, if you pass on some negative number, -5 to the sigmoid function, e power -5 by 1 plus e power -5, 0.001, almost close to 0. Means e power x, this tan hyperbolic function, sorry, the sigmoid activation function varies from 0 to 1, 0.99 and 0.001. Similarly, you have tan hyperbolic function also we use in LSTM. Just for our understanding purpose, I am telling this. Tan hyperbolic or hyperbolic tangent activation function. Look at this, the formula e power x minus e power minus x. You see tan hyperbolic theta, this is the formula, right? E power x minus e power minus x divided by e power x plus e power minus x. You substitute the value. Just yes, any doubts? No. So you substitute the value of our x. X is, let us say x is equal to 2. X is equal to 10 or whatever your wish. You will end up with 1. The value close to 1. Suppose if you if you put the value of x is equal to -5 or -10 or -20, any value you put, you will end up with minus. It will not exceed -1. That is the use of trigonometric functions, right? You want to reduce the value of the distribution or the data. You bring that inside the trigonometric function, It will be scaled between 0 to 1, minus 1 to 1, something like that. Okay, now you know, I have already told you. So at the top you have this. See, here you have a green color at the top. See, you will, if you look at this network, this one, this is a green color line, and here a purple color line at the bottom. Huh? So that the green color line at the top is this one. So this one, okay. So here what is happening? This is a lack of, so allows this lack allows the long, this we are using for updating the long term memory. I told you in LSTM we need to update both the long term memory as well as the short term memory. I am using this green color. This is going to represent. Okay. So similarly at the bottom, this is used for updating the short term memory. Short term memories are directly connected to weights. Long term memories are the one which are going to be series. So it will get updated only when you receive the output. It will get updated only when you receive the output. But here, short term memories are directly connected to weights, and you can initialize the weights. Okay. So at the, we are going to supply the input from bottom. We are going to supply input from bottom to short term memory, and we will predict, because the long term memory you cannot assume. At the beginning you can assume, but after that it will pass through activation function and it will reach. Okay. Then you will update the long term memory. So now you see, now we will divide. So this is the whole for this one. First I will take only forget gate. Means you have 5, 1, 2, 3, 4, 5. The first box is forget, next two box is input, next another two boxes output gate. So we will consider out of these 5 boxes, only the first box I will consider, and that first box I call it as forget gate. This first box I will call it as a forget gate. Where is this? This is the first box. This is the first box. So if you are finding it difficulty, anything you need clarification, stop me. You are free to stop. You are free to ask any question. Okay. Don't feel that you are not understanding something like that. Because understanding the logic is very important in LSTM. You will get a simple answer. That is different. Neural network you will get easily answer. Even if you don't understand, you will get very good result. That is not the intention here. We want you to understand. So here, look at this. I am initializing. Now we have plugged in some numbers. Let's do the math to see what happens in the first stage. See, this is what happening. So input I am taking. Input I am taking it as 1. Short term memory I am also taking it as 1. All these are assumed numbers, guys. 2.7, 1.63, 1.62. This is not calculated value. At the beginning of the process, you need to assume certain weights. So that is what I am assuming. 1.63, 2.7, 1.6. Okay. And this also, 2 also at the beginning. So what happens here? 1 into 2.7. Look at this. 1 into W1 into X1, W2 into X2, 1 into 1.63, plus bias I am adding. Bias is 1.62. This is the bias 1.62. W1 X1, W2 X2 plus bias, that is equal to output, that is going to turn out to be 5.98. This 5.98 is going to be fed inside the sigmoid function. So what is this I am discussing? I am discussing only about, I am discussing now only about this. We are discussing only this one. Forget gate. Next what we will discuss? Next I will discuss this one. This is this one. So anyhow, you don't do now I am just discussing about the forget gate. In forget gate only one sigmoid function is there. That I am discussing. See, here only one sigmoid function is. So initialized, weights are initialized, bias is added. So you got some output 5.95. This 5.595 is going to be fed inside the sigmoid function. Once I feed 5.95 inside the sigmoid function, look at this. What happens? This is the formula already you know, e power x by 1 plus e power x. So 5.95 divided by 5.95 plus 1 will is equal to 0.997. 0.997 means which is almost equal to 1. You keep this output with you. This is 0.997. Keep this output. So look at this. 0.997 came. What is this 0.997? This is the output coming from the see, this is the sigmoid function. So this is the output coming. See, this is the output coming from the sigmoid function, and that will be fed into the long-term memory. So look at this. That is what happening here. This is sigmoid function. So sigmoid function 5.95 passed inside the sigmoid function. We got 0.997, and this 0.997 earlier, this value 2 is assumed, and what I am going to do, I am going to pass on my output 0.99, means I am going to deduct 2 minus 0.997. I will get 1.99. Result is 1.1. So this is the first stage of LSTM. In a first stage of LSTM, what happens in first stage of LSTM? So unit reduced to long by a little bit. We are going to reduce the long term memory by little bit, because what happened so many years back, you need not consider everything, only few things if you consider, that is fine, but you have to consider, that is important. If you don't consider, that's a different thing, but how much you need to consider, so how much you need to forget, that is what is important. So this is why it is called as a forget gate. That is why it is called as, see, out of 2 you remember 1 point, you remember 2 minus 0.997. That is the, so case. So sorry, not minus, into how much you have to consider, means 2 into 0.997. Sorry guys, not multiplication, sorry, not subtraction, it is multiplication. So the value got little bit, okay, 1 point, yes, you should consider, not, no, may not be 100%, at least 90-95% you have to consider. So 1.99 you got, means yes, long term memory also given, important, short term memory also given, important, but in RNN short term memory was only given importance, long term memory was not given importance. You encountered vanishing gradient, exploding gradient problems. Okay, now this is over. Thus, thus, because the sigmoid activation function turns into a number of between 0 and 1. Okay, so suppose now earlier I considered input as 1, so here 1 into 2.7, 1 into 6.3. Suppose for this, if you consider the input as minus 10, so if I consider instead of 1, short term memory is earlier 1, long term memory I considered at the beginning 2, short term memory I considered 1, input to the network I considered 1 here earlier. Now I am considering input to the network as minus 10. What happens? So minus 10 into 1.63. All these things. So when you consider minus 10 here, what happens means the output coming from the sigmoid activation function will become 0. Maximum value is 1. Minimum value is 0. Means for a negative, if the weights are less than 1, if the weights are less than 1 or a negative number, our activation function, sigmoid activation function will become 0. Thus means 0 into anything, what is going to happen? 0 into anything, long, everything is 0. You will eliminate, you will forget everything, the long term, whatever happened. Okay, the output determines what percentage. So that is why whatever in the forget gate, the output coming from the forget gate determines how much percentage of long term memory is remembered, to be remembered. See how out of 2 I am remembering 1.99. So this is what I want to remember. How much you have to remember out of total? Out of 2 I am remembering 1.99. Out of 2 I am remembering 0. Okay, out of 2 I am remembering 0. So this forget gate will determine how much percentage you need to remember. Okay, any doubts are there till now? Kindly ask. Can I continue? Are you understanding? Please, Ankush, Salman, react, at least give me some answer here. I will be satisfied. Pushpa, Somshekhar,
Sir.
getting?
Yes. Yes, sir.
Ankush, getting, na?
Yes, sir.
Okay. So, now what I am going to do? Now what I am going to do? Here. Okay. Now this is over. Now I will go back. Now next is input gate. This one. This is the input gate. This I have to analyze. Okay. So on last final output. So now Out of 2 I am giving 1.99, that has to be remembered. Now I will go to input gate. So you have two blocks here in the input gate. You have two blocks in the input gate, right? You have two blocks in the input gate. And what are those two blocks? Let us see. Okay. So here 1.63, here also 1.63. 1.63 is common here. Here also I am taking 1.6. Is this input block? 1.6. Yeah, sorry. This is input. Where is this? Ah, here input block. Sorry, 1.63. This also assumed, guys. 1.65, 2.62. All these are assumed. This 0.94, 1.4, minus 0.13. All these are assumed because initially you have to assume the weights. Assumptions. Without assumptions, no neural network will run. Without assumptions, no neural network will run. So we need to assume. We need to assume. So this is what 1.6, 2.62, 0.94, 1.14, minus 0.32. All these things are there. So you have to see. You have sigmoid function, that is in the blue color box, and you have saffron color box. This is a tan hyperbolic function. So this is a sigmoid function and this is a tan hyper, means you have two functions here. So how it is going to work, let us see. So if you pass on the value, so here already input your sorry, where is this? Yeah, here you have 1 into 2, so input is 1. Input you are considering 1 into 2 plus 1 into 1.65, 1 here input is 1, here also input is 1 into 1.65 plus 0.62. Whatever the output is going to come, that you are going to feed inside the sigmoid function here also, and you will get some output. So how much output you got? So here how much output you will get? So that you will get some output here also, right? So 0.97 you got, 0.97. Next, how much point? So now what I am going to get here, see here what is happening. uh, Forget gate. See, look at this, input is 1, 1, 2, these are all initialized, 2, 1.65, 1.65, 0.62. Once then you are going to pass this inside the sigmoid activation function. Output you got as 1. Okay, means what is this? You pass 1, 1 into 2 plus 1 into 1.65, and you summation of all this is 0.62. 0.62 is passed inside the sigmoid function. Once you pass 0.62 inside the sigmoid function, you will get 1 and 1. So similarly, this 1 is also supplied for here, 1 is also supplied for here, and 1 into 0.94, 1 into 1.41, we will get minus 0.32, and this minus 0.32 passed inside the tan hyperbolic function, and you got 0.9. So percentage of memory to be remembered, potential long-term memory. So you got this here. So this is 0.97 and this is how much? So 1. This is 1 and this is 0.97. See what is this happening here? Look at this board. See, look at this. This is what is happening now. See, 1 e power x, 0.94, 1 into 1.4, 1 into 1.4, then 1 into 0.94. So minus, this is bias. Bias can be positive, bias can be negative. So 2.03, 2.03 passed inside the tan hyperbolic function, you will get 0.97. Okay. So 0.97. See, this you are passing a 0.93. So 2 you are passing to positive number. Suppose instead of positive number, if you pass x is equal to minus 10 inside the tan hyperbolic function, it will give minus 1. Means minus 1 to plus 1 tan hyperbolic function will vary. That you already know. Similarly, if you pass this inside the sigmoid function, you will get the output as 1. Similarly, if you pass this inside the sigmoid function, you are getting as 1. So 1 and 0.97. So what you are going to do? So what I am going to do here is 1 plus 0.97 is how much? What is this 1 plus 0.97? So next what I am going to do means that entire potential long term memory is retained because multiplying it by 1 doesn't change. See, here you have 1, you get, see, first is how much percentage of long term memory you need to remember, that you will find out. In the second one is the input gate you have both sigmoid function, tan hyperbolic function. In that input gate you will determine how much potential memory to remember, that is short term memory. Here it is a long term memory. And what is the potential long term memory also you will find, means how much potential long term memory is there, how much you are going to remember, that also you will find out. So means output coming from sigmoid function, tan hyperbolic function, how much is this, so what is this value, find out. What is this 1 plus 0.97? 1 plus 0.97 is how much? How much? 2 point, what is this, how much, 1 2.96 is how much, 1.99 you have here, 1.99 plus 0.97, okay, how much you get, see, you multiply this, see, you both have to multiply, is a into mark, you multiply potential memory to remember percentage. See, whenever you pass on one thing, you keep that in your mind, whenever is a passing through a sigmoid function, we will determine the percentage. Here also percentage, this is sigmoid function, potential of memory that needs to be remembered. Here we are talking about long term memory, but here we are extracting from the weight, that is short term memory, the potential memory. And here also potential, this is not percentage, but here when you pass inside the tan hyperbolic function, this will determine the potential long term memory. You multiply 1 into 0.97, output is 0.97, 1.99 plus 0.97, you will turn out to be 2.96, means long term memory was 2, then it got reduced to 1.99 in the forget gate after the input weights are initialized to start the network. So input gate, in the input gate, after going through sigmoid and tan hyperbolic function, this long term memory, new long term memory got enhanced to 2.96. 2.96. So until here, any doubts are there, you ask. Till input gate and forget gate is over, final gate is output gate. Any doubts are there till here? Ankush, Somsekhar, Pushpa, Salman, any doubts are there? Somsekhar, you are unable to hear you, man.
Sir.
Understood, huh?
Yes, sir.
Yes. So now, what I will do next is, so now 2.96, this is the new long term memory. The new long term memory is now 2. Next, this will go to the final stage. The output is 2.96. 2.96 is fed inside the tan hyperbolic function. See, good. Look here. So here, 1 minute, it's not coming. See here. Now, first two, see, forget gate is over. Then input gate is also over. What you have, only you have final stage. See, now the sum is directly fed. See, look at the green color at this. So here, this is fed into tan hyperbolic function. See here, first we will feed it to tan hyperbolic function, and then means we will consider what is this green color is getting input to tan hyperbolic function. Similarly, from the bottom, purple color short term memory is there. Bottom is short term memory, top is long term memory. That is also going to come. That will not go to tan hyperbolic function. Here it will go to sigmoid function. Then output of sigmoid function and tan hyperbolic function is multiplied, and that is the final output of the network. So that is what. See, look at this. Now, what is my new long term memory? This is my new long term memory. Where is this? This is my new long term memory. How much I got? Yes, 2.96 is my new long term memory. This is directly fed into the output gate. Say 2.96 is the new long term memory that I am going to feed inside this new long term memory. I am going to feed inside tan hyperbolic function. So 2.96 of tan hyperbolic x is equal to almost near to 1.99. Similarly, from the downward side, these are the weights initialized 4.93, 0.19, 0.59. This is going to be fed inside. This is initialized. This is going to fed inside the sigmoid function. Here also 0.99. 0.99 into 0.99, 0.98. 0.99 into 0.99, 0.99. And this is the new short term memory. New long term memory also I calculated. At the end I will calculated the new short term memory also. And this new short term memory is the new output. Means the immediate new short term means the previous one. So the new weight is the new value for the weights is 0.98. This is the output of the LSTM 0.98. This is the output gate. So this is the architecture of my LSTM. So now let us consider, okay, now let us consider one example, so for our better understanding. So let us say we have companies, we have company A and company B. So this company and A and company B are traded in the stock market, okay. So at the day one, company blue, that company A is a blue color company, company B is a green color company. In the day one, the company A was low, that is 0. Day 2 it was at the middle, and day 3 it was somewhere here, and day 4 it was high. Again in day 5 it was 0, low, right? Similarly, green company, day 1 itself it is high, day 2 and 3 they were in between, and in day 4 again it was high, day 5 also it was high. That is green color company. So now all of on all of the other days, day 2 see everything is same. Day 2, 3 and 4, both green company and blue color company is merging. Only on the first day, uh, the blue color company is low, green color company is high. On the last day, green color company is high, again blue color company is low. So now, okay, that you just keep that in your mind. So now what I have to do is, using this LSTM, what I have to do, I have to predict the things. I need to predict. So we are going to sequentially run the data from day 1 to day 4 through an LSTM. Let us run this through an LSTM. So day 1, and we will predict the 5th day. So you have the data for 5 days. Already you have. We will check. We will train the model for 4 days, and we will check the output for the 5th day. We will train the model for the 4 days, and we will check the output for the 5th day. So let us see, look at this guys. So day 1, so and this is the prediction, whatever that is there in the purple color, this is the predicted output. What is there in the purple color, this is the predicted output. So we can see it can correctly predict the value for the day 5 or not. So let us see for both the companies. So let us say, so let us assume the blue color company. Day 1 is 0, day 2 is 0.5, day 3 is 0.5, day 4 is 1, and day 5 is 0. Already we want to predict the value on the day 5. Already you know day 5 value is 0. Already you have the output. Now you want to check whether my LSTM network is going to predict this perfectly or not. So let us see. Let us say, let us initialize the things. Initialize the things. How it is going to be? See, initialize. See, if you assume, uh, if you assume uh, the weights, if you assume the weights, so how it is? How can I say this? 1 minute. Okay. Day 1 is 0. Initially, look at this. How we are going to initialize? Here I am saying as 0.5 now. For day 1, instead, let us forget about day 2. This is day 1. Day 1, instead of 0.5, I will put it as, see, this is 0. Day 1. Day 2, it is 0.5. Okay. Day 1, instead of 0.5, you keep in your mind, instead of 0.5, instead of day 2, you keep that in your mind, day 1. instead of zero point 0.5 it is 0. So what is this 0 into anything? So now you pass on this value inside the network. 0 into 0 into weight is 0, huh? And 0 into anything, what happens? See, you already know this, how this works. See, input get here. See this. Where is that? Where is my input get here? Here. See, 0. Here you are. Yeah, here only we have. Here you have 0, na? 0 is there here. 0 into 2 point something is 0. So in summation you will get 1.8. Once you pass this answer sigmoid function, when you are going to initialize, day 1 is 0, your sigmoid function 0.83. So long term memory I am assuming it as 0. Here also you got 0, and initialize some weights, some value you are going to assume. New long term memory you got -2, and the output you got as -0.3 when initial weights are for the day 1, when the day is 0. Day is 0 means when the day for the day 1 output is 0. Look at this, you already know. You assume day 1 output is 0 because it is low. Low means 0, high means 1, zero point 0.5 means middle value. So already output is 0 in the day 1. Next day output is 0.5. Why? Because in the day number 2 output is 0.5. Day number 1 output is 0. Day number 2 zero point 0.5 because it is at the middle, not 1. So if it is high, I will call this as 1. So day number 2 it is 0.5, and if you pass on this 0.5 in the neural network, the same output, instead of -0.3, how much you are going to get? The output you are going to get as some value. Output you are going to get as some sort of value. So earlier it was, now you are going to get it as -0.2. How you are going to get? So you are going to get some value. Similarly, you are going to long short term 0.3 -0.13. So new short term memory -0.13. Okay, 1 minute. You got this value. So for the day 1, this is low, and I got the output as -0.13. What is this new short term memory? Earlier I assumed the short term memory as 0. Now I got the short term memory as 0.13. I will replace this 0 with 0.13. That is what we have done. See, somewhere we have replaced. So we have replaced the value with 0.13, and if you run this 0.13, then you will get the output. So that is what we updated the short term. 0.13 means the here 0.13 is considered only one decimal place. 0.1 is considered. What is the new long term memory? Earlier I assumed 0. What is that I got? 0.2. 0.2 I am assuming now. For the next iteration, next cycle I am assuming 0.2. So 0.1, 0.2 you got from when you assumed as 0. Next when for the day 2 you are assuming it as 0.5, and the newly updated long term and short term memory is -0.1 and 0.2. You will get the output -0.3 -0.2. You will get the output -0.3 -0.2. So like this, if you keep on updating the things, so 0, 0.5, 0.2, 0.3, you will be able to predict. So we will be able to predict the exact output. So output you will get. See here on the day 4, if you keep on updating the weights, it correctly predicted as 0 on the day 4. Correctly predicted as 0. See, look at this 0. 0, 1, 2, 1, 2, 3, 4, and day 4, and the output you are on the day at the end output you are going to predict them as 5. So that is how. So LSTM correctly predicts. Also means that you can check it out. You have the mathematical equations. You can go through this and you can check it out. Definitely it will work. So this is about LSTM guys. So that is means Each weights gets updated. See, if you have any doubts, see 1 minute. See here minus zero point 0.3. I am going to put this minus zero point 0.1 and zero point 0.2. You get minus zero point 0.3 and zero point 0.2. This I am minus zero point 0.3 and zero point 2 I am updating here. You will get the weight. So now output you got 0 0 again. Output you got 0 and 0. So means that is the output you got for the this one. So like this you are going to get. So this is for output. Finally again if you pass on 0 and 0 here, everywhere you pass on 0 and 0, what happens? So next cycle, here also 0, here also 0. What is the short term memory weight, long term memory weight? So this you will repeat this cycle. Everywhere 0 means final output will be 0. The fifth day output will come to 0 because you multiply this 0 with long term memory also, short term memory also. You have to multiply everywhere. That is the meaning. That is why it will correct predictly. Company A it will correct predictly. The same way company B also you can predict the final value will come as 1. Okay. So this is about this LSTM network base. Means exactly how much percentage you need to remember. That is what it's going to predict. It will avoid the problem of vanishing gradient and exploding gradient problems. Okay. So this is regarding LSTM. Okay. So any doubts are there? Kindly